Right now, every atom inside your body is mostly empty space. The part that actually has mass, almost all of it, is a speck so tiny it makes the whole atom look enormous by comparison. Picture a football stadium. The atom is the stadium. The nucleus is a single grape in the centre, and inside that grape, physicists spent 80 years trying to figure out what was actually there. What they found changed everything. Layers inside layers. Forces stranger than anything you feel in daily life. Particles that can never be pulled free no matter how hard you try. We'll go from the first man who ever glimpsed the nucleus, to the machines that fired electrons like bullets into protons, to a force so bizarre it creates new matter when you try to break it. If you enjoy this journey, like and subscribe. It helps more than you know. Prepare yourselves. We begin.
Here is something that should bother you. Every solid object you have ever touched, a desk, a wall, a person, is almost entirely empty. The atoms that build all of it are more than 99.9% nothing. No matter, no substance, just open space. That sounds wrong. Things feel solid. They push back when you press them. But that feeling is electrical force between atoms, not atoms actually touching. At the scale where atoms live, solid and empty start to lose their meaning. So where is the mass? Where is the actual stuff? It hides in a place so small it almost doesn't exist. Every atom has a center called the nucleus. It holds more than 99.9% of the atom's entire mass. That is essentially all of it, and yet the nucleus takes up almost none of the atom's size. Its diameter is about 100,000 times smaller than the diameter of the full atom. To picture that, imagine the atom as a sphere the size of a professional football field. The nucleus sitting at the center would be roughly the size of a single grape. Everything else is empty. The electrons that orbit the nucleus are real, but they are almost weightless compared to the nucleus. An electron has about 1/1800th the mass of a proton. They contribute almost nothing to the atom's total weight. They do, however, take up the space around the nucleus. They create the outer shell of the atom, the part that pushes back when you press two objects together. That repulsion is why things feel solid, but the actual mass, the real substance of matter, lives in that grape-sized dot at the center. This creates a strange image. Imagine draining all the empty space out of every atom in the human body. What would be left is called nuclear matter. It would be so dense that a teaspoon of it would weigh roughly 1 billion tons. The entire human race compressed into its nuclei alone would fit inside a cube smaller than a grain of rice. That is how concentrated the nucleus is. Scientists did not always know this. For a long time, the best model of the atom imagined it as something soft, spread out, and uniform. Mass was thought to be distributed evenly across the whole structure. No one had seen evidence of a hard center. No one had looked closely enough. Then an experiment changed everything. It was one of the most surprising moments in the history of science. A team fired tiny particles at thin metal foil and expected them to pass through with barely a tremor. What happened next was something nobody predicted. Some of those particles bounced almost straight back. The person who designed the experiment later described his reaction. He said it was about as surprising as firing a large artillery shell at a piece of tissue paper and having it come back and hit you. That reaction told scientists something extraordinary was hiding at the center of the atom. Something dense, something almost impossibly small, something that had been there all along, completely invisible to every experiment that came before. That thing was the nucleus, and the man who realized it had no idea what it was made of. He only knew it existed. The question of what sat inside that tiny, violent core would take another 20 years just to get a basic answer, and almost a century to fully understand. What came next was stranger than anyone expected. Before anyone knew about the nucleus, there was a different idea about what atoms looked like. And the strange thing is, it was a reasonable guess. In the early 1900s, scientists already knew one thing about atoms. They contained electrons. The electron had been discovered in 1897 by a British physicist named J.J. Thomson. He proved that atoms had tiny negatively charged pieces inside them. That was a breakthrough, but it created a new problem immediately. Atoms are electrically neutral. They carry no overall charge. So if electrons are inside the atom and they are negative, something positive had to be in there too, and the positive charge had to be spread around in a way that balanced the electrons perfectly. Thomson proposed a model. He imagined the atom as a sphere of positive charge, soft and evenly spread, with electrons embedded throughout like blueberries in a muffin. The atom would be a kind of cloud of positive charge, and the electrons would sit inside it, dotted around in fixed positions, held in place by the balance of forces. This model had a nickname. People called it the plum pudding model. It sounds almost funny now, but in 1904 it was published seriously and received seriously. Thomson had discovered the electron. He had earned enormous trust in the scientific world. And his model was not a wild guess. It was built on the information available at the time. The plum pudding model had specific predictions. If atoms were soft clouds of charge with embedded electrons, then particles fired at those atoms should pass through without much trouble. They might wobble a little, they might deflect slightly, but nothing inside the atom would be hard enough or dense enough to push a particle back with serious force. That prediction seemed fine, until someone actually tested it. The experiment designed to test it was not even meant to disprove Thomson's model. The scientists running it expected to confirm it. They expected particles to drift through the foil with small deflections. Matching the soft cloud picture, the results were going to be routine, a bit of data, a confirmation. They got something else entirely. When the results came in, the deflections were not small and gentle. Some particles scattered at extreme angles. A tiny fraction came back almost the way they had gone in. That data destroyed the plum pudding model in a single experiment. A soft, spread-out atom could not do that. Only something hard, small, and concentrated at the center could. J.J. Thomson was wrong, and his own student was the one who proved it. That student would go on to become one of the most important figures in the history of physics. His name was Ernest Rutherford, and the experiment he designed with his colleagues, the one that broke the plum pudding model and revealed the nucleus, remains one of the most dramatic moments in the history of science. But here is what most people miss about that story. Rutherford did not set out to find the nucleus. He was testing a dead man's theory. He was confirming what he expected to be true. And then reality surprised him completely. What he found hiding at the center of the atom was something no model had predicted. The experiment that changed physics forever happened in a lab in Manchester, England, around 1909. Ernest Rutherford was leading the team. Two of his colleagues, Hans Geiger and Ernest Marsden, carried out the physical work. The setup sounds simple. What it revealed was anything but. The team had a radioactive source that fired alpha particles. Alpha particles are small bundles of matter, each one made of 2 protons and 2 neutrons, that shoot out of certain radioactive elements at high speed. They carry positive charge and they have real mass, much more mass than an electron. They are fast and they are heavy at the atomic scale. Rutherford's team aimed a stream of these particles at an extremely thin sheet of gold foil. Gold was chosen because it could be pressed into sheets almost unimaginably thin. Thin enough that only a few hundred atoms stacked up between one side and the other. If any material would let particles pass through cleanly, this was it. Around the foil, the team arranged detectors. These were screens coated with a material that lit up with a tiny flash whenever an alpha particle hit them. By watching where those flashes appeared, the scientists could measure exactly what angles the particles came out at after passing through the foil. The prediction based on Thomson's model was simple. Almost all particles would pass straight through. A few might bend a little. Nothing dramatic. What actually happened was different on every level. Most particles did pass straight through, which fit the prediction. But a small number deflected at surprisingly large angles, some bent at nearly 90 degrees, and a very small fraction, less than 1 in every 8,000 particles fired, bounced almost directly backward. Geiger reportedly told Rutherford that he had seen particles bouncing back. Rutherford's response became one of the most quoted lines in all of physics. He described it as the most surprising event of his life in science. He said it was as if a large artillery shell had bounced off a piece of tissue paper. Think about that for a moment. A fast, heavy particle fired with real energy, hitting something and coming back the way it came. What kind of object could cause that? A soft cloud of spread out positive charge would not do it. A diffuse blob of atoms would not do it. Something small, concentrated, and incredibly dense would. Rutherford spent months working through the mathematics. He needed to know exactly what kind of object would produce that pattern of deflections, most particles passing through, a few bending sharply, a rare few bouncing all the way back. His calculations pointed to one answer. Almost all of the atom's positive charge and mass had to be concentrated in a space far smaller than the atom itself. A tiny, hard, dense center. Rutherford published his nuclear model in 1911. The nucleus had been discovered. But here is what nobody talked about as much. Rutherford had proved the nucleus existed. He had shown where the mass was. He had no idea what it was made of. The nucleus was a confirmed fact and a complete mystery. At the exact same moment, they had no idea what lived inside it. And that mystery was about to get much stranger. 1 in 8,000. That was the fraction of alpha particles that bounced backward in Rutherford's experiment. 1 in 8,000 sounds rare, and it was. But in physics, rare events carry enormous information. That small number was enough to rewrite our picture of matter. Here is why. If the atom were a uniform blob, positive charge spread softly throughout. An incoming alpha particle would feel a gentle push from many directions at once. Those forces would partly cancel out. The particle might bend a little, but nothing in that soft cloud would be strong enough or concentrated enough to throw it backward. The math is clear on this. A diffuse atom cannot bounce a heavy particle. For a particle to bounce almost all the way back, it has to hit something small, dense, and carrying a concentrated positive charge. When a positive particle flies straight toward another concentrated positive charge, the repulsion builds fast and hard. If the target is heavy enough to stay put, the incoming particle gets thrown back the way it came. That is what was happening in the gold foil experiment. The rare backward bounces happened when an alpha particle flew almost directly at the center of a gold atom and hit the dense nucleus head-on. It was like rolling a bowling ball at a wall and watching it bounce back. The wall is small, and most of the room is open, so most balls roll past, but occasionally one hits the wall dead center. Rutherford's calculations predicted exactly this. He modeled the nucleus as a tiny, dense, positively charged object and worked out what scattering pattern that object would create. The predicted pattern matched the data precisely. That match was the proof. The atom had a core. That core was tiny beyond normal imagination, and it held almost all the mass. But a new question arrived the moment the nucleus was confirmed. If the nucleus carries positive charge, what is it made of? Positive charge in atoms comes from protons. So is the nucleus just a collection of protons? That guess ran into problems fast. Helium, for example, has 2 protons, but its nucleus weighs about 4 times as much as a single proton. If the nucleus were only protons, helium would weigh twice as much as hydrogen. It weighs 4 times as much. Something was providing extra mass without extra charge. The gap between mass and charge showed up across the periodic table. Carbon has 6 protons, but its mass is roughly 12 times that of a single proton. Every heavier element had this same pattern. There was too much mass and not enough charge to account for it with protons alone. This was a serious problem. Scientists spent the next 2 decades trying to figure out what was hiding inside the nucleus, alongside the protons. Some thought trapped electrons might be the answer. Maybe protons and electrons packed tightly together could produce the right mix of mass and charge. It sounded reasonable. It was wrong in ways that would take years to fully understand. The real answer came from a particle that nobody had found yet. A particle with mass but no electric charge at all. Something so neutral it left no trail and barely reacted with anything. Finding it would require a scientist willing to chase an invisible ghost, and the patience to look for something that refused to announce itself. Stand at the edge of a football field. Look at the far end zone. Now imagine the entire atom as that football field. Everything from goal line to goal line. Every blade of grass. The whole thing. The nucleus is a grape, sitting at the 50-yard line. Everything else, the space between the nucleus and the outer edge of the atom, is empty. This is not poetic exaggeration. The nucleus really is about 100,000 times smaller than the full diameter of the atom. In terms of volume, the nucleus takes up roughly 1/10 trillionth of the atom's total space. The rest is open, with electrons moving through it. That image should feel strange. Matter is mostly empty space. The thing that gives matter almost all its weight is a dot, and that dot exists in a state of constant violent tension. Here is why. The nucleus contains protons. Protons carry positive electric charge. Like charges repel each other. This is one of the most basic rules in physics. Put 2 protons next to each other, and they push apart. Hard. Put dozens of protons into a space smaller than a grape, and the repulsion between them becomes enormous. In a uranium atom, the nucleus holds 92 protons, all of them positively charged, all of them crammed into a space roughly 8 femtometers across. A femtometer is 1/millionth of 1/billionth of a meter. The electric repulsion inside that nucleus is extreme. So why does it not explode? This is the question that kept physicists up at night after the nucleus was confirmed. Something had to be holding those protons together against the enormous force trying to push them apart. That something had to be stronger than the electric repulsion. And it had to work only at the tiny distances inside the nucleus, because atoms don't just grab onto each other and fuse in normal matter. The answer would eventually be called the strong force. But in the early decades after Rutherford's discovery, scientists didn't have that answer yet. They just knew the nucleus should not hold together, and somehow it did. There was also the mass problem. The nucleus contained too much mass for protons alone to explain. For every element heavier than hydrogen, the numbers didn't add up. Something else was in there. Something massive, something neutral, something that left no electrical footprint and slipped past every detector available at the time. Scientists knew the something had to exist. They could see its absence in the mass calculations, but they couldn't detect it directly. It became a kind of phantom, a necessary piece that refused to show itself. And it wasn't just missing from experiments. The phantom's absence left the entire theory of nuclear structure incomplete. Without it, no one could explain what nuclei were actually built from. Atoms were confirmed to have a nucleus. The nucleus was confirmed to have protons, but the proton count alone couldn't explain the weight. For 20 years after Rutherford, the nucleus sat in physics like a locked room. Scientists knew something was inside. They couldn't open it. Then one researcher followed a strange experimental result that everyone else had ignored and found the missing piece. Something was wrong with the numbers. Scientists knew it as early as 1913. Right after Rutherford confirmed the nucleus, physicists began trying to figure out its contents. Protons were the obvious candidate. A proton carries exactly the positive charge that makes up the nucleus. Hydrogen has 1 proton, and its nucleus has 1 unit of positive charge. That checks out. But when scientists looked at helium, the problem appeared immediately. Helium has 2 protons. Its nucleus should weigh about twice as much as a hydrogen nucleus, if protons are the only ingredient. Helium's nucleus actually weighs about 4 times as much as hydrogen's. Double the charge, 4 times the mass. That gap did not go away with heavier elements. It got worse. Carbon has 6 protons. Its nucleus is 12 times heavier than a hydrogen nucleus. Nitrogen has 7 protons. Its nucleus is 14 times heavier than hydrogen. The pattern was consistent. Heavier elements always had roughly twice as much mass as their proton count alone could explain. Something was adding mass without adding charge. At first, the guess was that electrons were the answer. If protons and electrons were packed tightly together inside the nucleus, a combination of the two could produce the right mix of mass and charge. A proton and an electron together would cancel out electrically, giving a neutral unit of mass. Pack enough of those in alongside the free protons, and the mass and charge numbers could be made to fit. It sounded plausible, but the deeper scientists looked at it, the more things went wrong. Electrons inside the nucleus created serious problems. The math of quantum mechanics, the rules governing tiny particles, said electrons confined in a space as small as the nucleus would carry enormous energy, far more energy than the nucleus could contain. An electron crammed into nuclear dimensions would be moving so fast and carrying so much energy that the nucleus could not hold it. There were also problems with spin. Protons and electrons each carry a property called spin. When physicists measured the spin of certain nuclei and compared those measurements with what a proton-electron mix would predict, the numbers disagreed. The nuclear spins came out wrong. So the electron hypothesis quietly failed, but nothing replaced it. The mystery mass had no candidate. Scientists were certain something neutral and massive was inside the nucleus. No one could find it. Then, in the early 1930s, a series of experiments in Europe started producing strange results. A German team fired radiation at beryllium and created a new type of ray. Those rays were penetrating. They passed through matter easily, but they carried no electric charge, so no one could detect them directly. When those rays hit atoms, they knocked protons out with surprising force. Most physicists assumed the mystery rays were energetic gamma rays. James Chadwick disagreed. He thought the energy transfer didn't match gamma rays at all. He ran calculations and came to a different conclusion. The rays were particles, neutral particles, particles with almost the same mass as a proton. He had found the ghost. What came next, and what those neutral particles meant for the entire picture of matter, was a shift that physicists had not seen coming. Before James Chadwick found the neutron, scientists were working with a broken model and trying not to admit it. The idea was this: the nucleus contained protons and electrons packed together. Protons brought the positive charge, electrons cancelled some of it out and added a bit of mass. Adjust the ratios correctly, and you could account for any nucleus in the periodic table. On the surface, it almost worked. The numbers for mass and charge could be balanced, roughly, with the right combination. And since electrons had already been found inside atoms, putting them inside the nucleus didn't seem like a huge leap. But the problems were not small, they were fundamental. The first problem was energy. Quantum mechanics, the rulebook for particles at tiny scales, has a principle called the uncertainty principle. It says that the more tightly you confine a particle to a small space, the more energy that particle must carry. An electron forced into a space as small as a nucleus would carry far more energy than any known nuclear process could explain. The numbers were off by a huge amount. Nature simply would not allow a low-energy electron to stay trapped in something so small. The second problem was spin. Spin is a property that particles carry, and it follows strict rules. When physicists measured the spin of nitrogen's nucleus, They got a result that didn't match what a proton-electron combination would produce. Nitrogen has 14 protons and 7 electrons in the nucleus under the old model. The combined spin of those 21 particles should give a half-integer result. Experiments showed an integer. The model gave the wrong answer. The third problem was magnetic behavior. Electrons have a specific magnetic property. If electrons lived inside nuclei, nuclei should show that magnetic signature. They didn't. The magnetic measurements from nuclei were completely inconsistent with electrons being permanent residents in there. 3 separate types of evidence, all pointing the same direction. Electrons did not belong inside the nucleus. But if not electrons, then what was providing the extra mass? The proton-electron model was broken. No replacement existed. The nucleus held a gap that nothing could fill. Some physicists proposed a combined particle, a proton and electron bound so tightly together they acted as a single neutral unit. This was essentially predicting the neutron without naming it. Rutherford himself had speculated along these lines as early as 1920. He called it a possible neutral doublet, but he couldn't produce one or detect one. It remained speculation. The experimental clue that broke everything open came from researchers in France. Irene and Frédéric Joliot-Curie fired alpha particles at beryllium and noticed that the radiation produced could knock protons out of hydrogen with enormous force. They published their results and described the radiation as gamma rays. Chadwick read their paper and immediately suspected they were wrong. Gamma rays don't transfer energy to protons that efficiently. The math didn't work. Something heavier was doing the hitting. He designed his own experiment, measured the collisions carefully, and ran the calculations. A particle with nearly the same mass as a proton, carrying no electric charge, explained the data perfectly. In February 1932, Chadwick published his discovery of the neutron. The locked room inside the nucleus had finally opened. What was inside it, and what that meant for everything else, was only starting to come into focus. James Chadwick was not chasing the unknown when he made his discovery. He was chasing a mistake made by someone else. In early 1932, he read the paper from Irene and Frédéric Joliot-Curie describing the mysterious radiation produced when alpha particles hit beryllium. The Joliot-Curies had done careful work. They had measured the energy of protons knocked loose by this radiation. They concluded it was gamma radiation, high-energy light, with no mass. Chadwick looked at the energy numbers and said quietly that this was impossible. Gamma rays transfer energy through a process involving their electric field interacting with charged particles. To knock a proton out of hydrogen with the energy the Joliot-Curies reported, the gamma rays would need to carry far more energy than the original alpha particle source could possibly produce. The numbers violated conservation of energy. Chadwick had another idea. He was already primed for it. Rutherford had speculated about neutral particles years earlier. Chadwick had been quietly looking for experimental evidence ever since. He set up his own experiment. He placed a source of polonium next to a piece of beryllium. The alpha particles from the polonium hit the beryllium and produced the mystery radiation. Chadwick then placed various target materials, hydrogen-rich paraffin wax, nitrogen gas, lithium, in the path of the radiation and measured how much energy was transferred to knocked-out protons and nitrogen nuclei. If the mystery radiation was massless gamma rays, the energy transfers would follow one pattern. If it was a stream of neutral particles with mass, the transfers would follow a different pattern. The calculations were precise enough to tell them apart. The data matched the neutral particle model perfectly. A particle with almost the same mass as a proton, carrying no electric charge, explained every measurement. Chadwick published his discovery in February 1932, less than 3 weeks after starting the experiments. The speed was unusual, he was confident in the data, and the implications were clear. He called the particle the neutron. Detecting it required an indirect approach because the neutron carries no charge. It doesn't leave a track in a detector. It doesn't cause an electrical signal on its own. You can only see what it hits. Chadwick measured the neutron's existence through the motion of the things it knocked into. It was like proving a ghost existed by measuring the objects it moved. That indirect detection method would become important again decades later, when scientists faced a similar problem with an even harder-to-see type of particle. The neutron completed the basic picture of the nucleus. Protons give charge, neutrons give mass without charge. The ratio of protons to neutrons determines the element and the specific version of that element. A nucleus with 6 protons is always carbon. A nucleus with 6 protons and 6 neutrons is one kind of carbon. 6 protons and 8 neutrons is a heavier version of carbon that happens to be radioactive. The full periodic table, the isotopes, the mass discrepancies, all of it collapsed into a clean framework in 1932. But something larger was still missing. The nucleus now had its ingredients. No one yet knew the recipe that held them together. And holding protons together at nuclear distances was a problem that made the proton-electron puzzle look simple. The moment Chadwick published his discovery of the neutron, a cascade of problems in nuclear physics solved themselves almost overnight. The mass discrepancy disappeared first. Helium has 2 protons and 2 neutrons. Its nucleus weighs about 4 times a hydrogen nucleus. That makes sense now. 2 protons plus 2 neutrons equals 4 particles of similar mass. Carbon has 6 protons and 6 neutrons. Its mass is 12 times hydrogen's. The pattern works. Element after element falls into place once the neutron is in the picture. The charge accounting works too. The number of protons gives the positive charge. The neutrons contribute mass, but nothing to the charge balance. Helium's nucleus carries 2 units of positive charge because it has 2 protons, not 4. Carbon carries 6 units of positive charge for the same reason. The discrepancy between mass and charge that had confused scientists for 2 decades was gone. Isotopes, different versions of the same element, made sense at last. An isotope is just a nucleus with the same number of protons, but a different number of neutrons. Carbon-12 has 6 protons and 6 neutrons. Carbon-14 has 6 protons and 8 neutrons. Both are carbon because both have 6 protons. The chemical behavior is almost identical. The mass is different. That was always known, but now it had a clean explanation. The awkward proton-electron model of the nucleus could be abandoned completely. Electrons no longer needed to live inside the nucleus as permanent residents. The nucleus was protons and neutrons, full stop. The German physicist Werner Heisenberg worked out the mathematics of this new 2-particle nucleus almost immediately after Chadwick's announcement. Heisenberg showed that protons and neutrons could be treated as 2 versions of a single type of particle, distinguished mainly by their electric charge. He called the underlying particle the nucleon. That name stuck. But Heisenberg's work also sharpened the central unsolved problem. If the nucleus is protons and neutrons, what holds them together? Protons repel each other through electric force. Neutrons don't repel anyone electrically, but they don't attract anything through electricity either. Gravity is nowhere near strong enough at atomic scales to hold particles together at nuclear distances, and yet the nucleus holds. Something was acting between nucleons, something powerful, short-ranged, and unlike any force then known to science. Heisenberg proposed that the binding force might involve an exchange of something between protons and neutrons. Japanese physicist Hideki Yukawa, working in 1935, built on this idea and predicted that a new particle, one nobody had found yet, might be carrying the force between nucleons. He predicted its mass. He predicted its properties. Nobody could find Yukawa's particle for years. When they eventually did find something close, it turned out to be the wrong particle. The actual carrier of the nuclear binding force would take decades more to understand fully. The picture was getting cleaner at the nuclear level. But below that level, something far stranger was waiting. Something that would rewrite the rules of how physicists even thought about matter. The nucleus had contents. The contents had a binding force. And that force had a source that nobody yet understood. Take a magnet, flip it around, and try to push the same poles together. You feel the resistance. The closer you push, the harder it fights back. Now imagine that same repulsion, but 100 million times stronger, inside a space smaller than anything you can see with the best microscope ever built. That is what every nucleus is dealing with right now. Every proton in a nucleus carries positive electric charge. The rule of electromagnetism is simple and absolute. Like charges repel. Two positive charges push apart. The force between them grows stronger as they get closer together. In a nucleus, the protons are not just close. They are crammed into an unimaginably small space. A typical nucleus is a few femtometers across. A femtometer is 1/millionth of 1/billionth of a meter. At that distance, the electric repulsion between two protons is enormous. Scientists call this the Coulomb barrier, the wall of electric force that positively charged particles have to overcome to reach each other. In a large nucleus like uranium, 92 protons are packed into that tiny space. Every proton is pushing away from every other proton simultaneously. The total repulsion inside a uranium nucleus, if you tried to calculate it as a force at human scale, would be extraordinary. The nucleus should tear itself apart in an instant. And yet uranium atoms exist. Gold atoms exist. The nucleus holds. Something is stronger than the Coulomb repulsion at short range. Something cancels it out, or overpowers it, and binds the protons and neutrons together despite everything the electric force is doing to push them apart. That something had to satisfy very specific conditions. It had to be attractive, pulling nucleons together. It had to be far stronger than electric repulsion at the distances inside the nucleus. And it had to drop off extremely rapidly with distance. Because nuclei don't just spontaneously grab onto each other in ordinary matter. Atoms stay separate. Molecules stay separate. The binding force had to have a very short reach. All of this was known by the mid-1930s. Scientists had the shape of the force. They didn't have the mechanism. Yukawa's idea in 1935 was that nuclear forces might work through particle exchange, similar in principle to the way electric forces could be understood through the exchange of photons. Yukawa predicted a carrier particle, medium mass, that would shuttle back and forth between nucleons and create the attractive binding force. When cosmic ray experiments found a new medium mass particle in 1937, physicists thought they had found Yukawa's carrier. They hadn't. That particle, the muon, barely interacted with nuclei at all. It was something else entirely. The real carrier of the nuclear binding force between nucleons was called the pion, and it wasn't confirmed until 1947. But even finding the pion only pushed the question deeper. What was the pion? Why did it exist? What was the nuclear force really made of at a more fundamental level? Those questions would only be answered after scientists looked deeper, far deeper, than the proton and neutron themselves. What they found inside the proton was nothing like anyone had imagined. Most people have heard of gravity. Most know about electricity and magnetism. Some know there are forces that govern radioactive decay. But the strongest force in nature, the one that keeps every nucleus from flying apart, is almost completely invisible in daily life because it works only across distances shorter than a proton's diameter. It is called the strong force, or the strong nuclear force. Its range is roughly 1 femtometer, that is about 1/millionth of 1/billionth of a meter. At that scale, the strong force is powerful enough to overcome the electric repulsion between protons and hold them tightly inside the nucleus. Beyond that scale, even just a few femtometers away, the strong force drops to essentially nothing. This is completely unlike gravity or electromagnetism. Gravity and electric forces weaken with distance, but they never fully turn off. They follow an inverse square law. Double the distance, and the force drops to 1/4. The strong force behaves differently. It stays strong across nuclear distances, and then vanishes almost completely once particles move slightly farther apart. Think of it like superpowered tape. At touching distance, it holds tight. A millimeter away, it does nothing at all. This short range is precisely why nuclei exist, but don't just keep absorbing every proton and neutron they encounter. The strong force pulls nucleons together once they are close enough, but it can't reach out across the empty space between atoms to pull atoms into each other. At the distances inside a nucleus, the strong force beats the electric repulsion handily. A proton inside a nucleus is simultaneously being pushed away by the electric force from every other proton and being pulled back in by the strong force from neighboring nucleons. The strong force wins, barely in large nuclei. That balance is delicate. Push too many protons into a nucleus without enough neutrons, and the electric repulsion wins. The nucleus decays. In the 1930s and 40s, the strong force was understood only as a force between protons and neutrons. Physicists could measure it, model it, and make predictions with it. But they didn't know what created it or why it existed. The answer turned out to require a completely different level of reality. The strong force that acts between protons and neutrons inside the nucleus is not the deepest version of itself. It is actually a side effect, a leak of something happening at an even smaller scale inside the protons and neutrons. Understanding the true nature of the strong force required discovering what protons and neutrons are actually built from. That discovery started not with nuclear physics, but with an explosion of new particles that nobody expected. A zoo of strange new matter appearing in accelerator experiments around the world, crowding the lab results with objects nobody could explain. The more physicists looked, the messier matter became. And the mess was a clue. The strong force does not follow the rules that other forces follow. And that difference is what makes the nucleus possible. Most forces in nature get weaker as distance increases. Pull two magnets apart, and the attraction fades. Move away from a charged object, and the electric field weakens. Gravity drops off as you climb higher. The pattern is consistent across electromagnetism and gravity. More space means less force. The strong force runs on different rules entirely. At very short distances, the kind found inside a proton, the strong force actually loosens. Quarks close together inside a proton feel relatively free. They move around. They don't feel locked in place. Physicists call this property asymptotic freedom. At short range, the strong force relaxes. But as the distance increases, something different happens. The strong force does not fade the way electricity or gravity does. Instead, it stays roughly constant. Imagine stretching a rubber band. As you pull it farther, the resistance doesn't decrease. It grows. The strong force behaves like that rubber band, except with a dramatic ending. If you try to pull two quarks apart, the force holding them together stays strong as the gap grows. At a certain point, enough energy has been stored in the force field between them that something extraordinary happens. The energy converts into new matter. A new quark-antiquark pair pops into existence from pure energy, and suddenly, instead of two free quarks, you have two new pairs of quarks, each bound together. You tried to isolate a quark, you ended up with more bound particles. This is why quarks have never been found alone. Every attempt to separate them creates new combinations instead of free pieces. Nature refuses to let them exist in isolation. For the nuclear force between protons and neutrons, the rubber band analogy applies in a modified way. The protons and neutrons inside a nucleus are already composite objects. Each one is three quarks bound together. The force between whole protons and neutrons is a kind of spillover from the deeper quark-level force. Like the way a strong magnet near a pile of iron dust attracts not just individual atoms, but clumps of atoms through a broader magnetic effect. The nuclear force, the one holding the nucleus together, is actually a residual effect of the quark-level strong force acting between composite particles. That distinction matters because it explains why the nuclear force has the particular short range and specific behavior that it does. At the proton-neutron scale, the strong force acts through particle exchange, specifically through particles called pions and other mesons. At the quark scale, it acts through a different carrier altogether, called the gluon. These two levels, the nuclear force between nucleons and the quark-level force inside nucleons, are connected but distinct. Understanding one required going all the way down to the other, and going that deep required machines more powerful than anything science had built before. By the 1950s, particle physics had a problem it had not expected. The problem was too many particles. When cosmic rays, high-energy particles from space, hit the atmosphere, they created collisions energetic enough to produce new types of matter. Scientists found particles that had never been seen before. They had strange properties that didn't fit the known picture. They decayed in unexpected ways and produced signals that didn't match the existing theories. Then particle accelerators began running, machines that smashed protons and electrons together at high speeds started producing the same types of strange particles, and more. The list grew. Every few months, someone announced a new particle, then another, then clusters of them. By the early 1960s, there were dozens of strongly interacting particles known. Scientists gave them names and tried to track their properties. They were grouped into a category called hadrons, particles that feel the strong force. But there were so many of them, and they seemed so different from each other, that no simple pattern emerged. Some were called mesons, others were baryons. Some were heavy, some were light. Some decayed quickly, some lasted longer. Some had electric charge, some were neutral. Some had unusual quantum properties that physicists described as strange, which eventually became a technical term in the theory. The situation became known informally as the Hadron Zoo. A zoo is what you call a collection of animals when you don't understand the organizing principle. Each species looks different. Each behaves differently. Before taxonomy in biology, a zoo was just a collection of confusing creatures. That was exactly how particle physics felt by the early 1960s. Dozens of particles, no unifying rule, no obvious reason why these particular objects existed, and not others. When science is flooded with too many pieces, it usually means the pieces are not fundamental. Chemists once struggled with a similar problem. Before the periodic table, there were dozens of substances with different properties and no clear pattern. Then scientists realized the substances were combinations of a smaller set of elements. The apparent chaos had a hidden order underneath. Particle physicists began to suspect the same thing. If the Hadron Zoo had so many members, maybe those members were not fundamental particles at all. Maybe they were combinations of something smaller. Maybe there was a level of reality beneath the proton and neutron, a deeper layer that nobody had reached yet. This suspicion led two physicists working independently to a proposal that seemed almost too simple and too strange at the same time. The proposal would eventually explain the entire Hadron Zoo in a few lines, but it would also require accepting something that went against every instinct physicists had built up over decades. The particles had inner structure, and the pieces inside them had never been seen outside them. Murray Gell-Mann was one of the most gifted physicists of the 20th century, and he had a habit of finding order where everyone else saw chaos. In the late 1950s and early 1960s, Gell-Mann looked at the Hadron Zoo and didn't see a mess. He saw a pattern trying to emerge from underneath the noise. He noticed that if you arranged certain hadrons by their charge and a property called strangeness, a quantum number that physicists had introduced to account for certain strange decay behaviors, the particles lined up in geometric groupings, triangles, octets, specific shapes on a mathematical chart. Gell-Mann published his classification system in 1961. He called it The Eightfold Way, a nod to a Buddhist concept about paths and patterns. The name was playful, but the mathematics was rigorous. The Eightfold Way organized all the known hadrons into families: 8 mesons in one group, 8 baryons in another, 10 baryons in a third. The groupings were precise, and the mathematical structure underlying them was a type of symmetry that physicists recognized from abstract algebra. But the most striking thing was a gap. In one of the predicted groupings of 10 baryons, only 9 were known at the time. The mathematical structure demanded a 10th particle with specific properties: a particular charge, a particular mass, a particular strangeness. Gell-Mann predicted it publicly at a conference in 1962. 2 years later, an experiment at Brookhaven National Laboratory found exactly that particle, with exactly those properties. The prediction had worked. A successful prediction like that is not a coincidence. It means the underlying structure is real. The Eightfold Way was not just a convenient filing system. It was pointing at something true about the nature of hadrons. Gell-Mann went further. He asked, what mathematical structure would naturally produce those groupings? The answer from group theory suggested that hadrons could be understood as combinations of 3 more fundamental objects. Gell-Mann called them quarks, a word he borrowed from a novel by James Joyce, for reasons he found amusing. George Zweig, working independently at CERN at the same time, arrived at the same idea through different reasoning. He called his proposed constituents aces. The name didn't stick. Quarks did. The quark model gave every hadron in the zoo a composition. Mesons were pairs, 1 quark and 1 antiquark. Baryons were triplets, 3 quarks. Protons and neutrons were baryons. Every known hadron could be built from combinations of 3 types of quarks. The hadron zoo had a genetic code, but there was a severe problem. The quarks that explained the zoo had properties that violated everything physicists expected. Their electric charges were not whole numbers, they were fractions. That had never been seen in nature before, and for many physicists, it made the entire idea feel suspicious. Quarks were not accepted easily. The reaction from much of the physics community in the 1960s ranged from skeptical to openly dismissive. The reason was one specific property that quarks were required to have: fractional electric charge. Every particle ever observed had an electric charge that came in whole number units. An electron carries 1 unit of negative charge, a proton carries 1 unit of positive charge, a neutron carries 0. That pattern had held across every experiment, every particle, every measurement. Charge came in integers. Quarks broke that rule. To explain the hadron zoo through quark combinations, the quarks themselves had to carry charges of positive 2/3 and negative 1/3. A proton is built from 2 quarks with charge positive 2/3 and 1 quark with charge negative 1/3. Add those up, and you get exactly 1 positive unit. A neutron is built from 1 quark with positive 2/3 and 2 quarks with negative 1/3. That adds to exactly 0. The math worked, but the charges required were fractions. No experiment had ever detected a free particle with fractional charge. If quarks existed as real objects, someone should have seen one by now. Searches ran immediately. Physicists looked through cosmic ray data for fractionally charged particles. They ran accelerator experiments, specifically designed to find free quarks. They analyzed old data, looking for signatures. Nothing turned up. No lone quark with fractional charge was ever detected. This created a strange situation. The quark model explained the hadron zoo with remarkable precision. Gell-Mann's predicted 10th baryon had been found. The mathematical structure worked everywhere it was tested, but the fundamental pieces of that structure could not be found as free particles. The reaction split the physics community. Some physicists treated quarks as purely mathematical tools, useful for organizing the zoo, but not necessarily real objects, something like a convenient accounting trick. you could calculate with quarks without believing they actually existed inside protons. Others thought the quarks were real but somehow permanently confined. Maybe the rules of the strong force meant that quarks could never escape from the combinations they were found in. Maybe isolation was simply forbidden by whatever mechanism bound them together. That second camp was right, but proving it required a completely different type of experiment, not searching for free quarks in detectors, but probing the inside of the proton directly, firing particles into protons at high enough energy to see if anything hard and point-like was hiding in there. The machines capable of doing that were just becoming available in the mid-1960s, and the scientists who ran those experiments were about to find something that changed physics forever. The proton, the particle that defined nuclear charge, turned out to be not fundamental at all. It had an interior, it had structure, and the structure inside it was about to announce itself in the most direct way experimental physics could produce. The idea that electric charge could come in fractions was not just surprising, it was, to physicists at the time, almost physically offensive. The unit of electric charge, the charge of a single proton or electron, had been measured for decades. In 1909, Robert Millikan suspended tiny oil droplets between charged plates and measured the force on them precisely enough to determine the charge of a single electron. That value, now known as the elementary charge, appeared in every equation. It was the atom of electricity, the smallest possible unit. Nobody had ever found anything smaller. Quarks required something smaller. 2/3 and 1/3 of that fundamental unit. If quarks were real, they carried less charge than the smallest charge anyone had ever measured. That wasn't just a technical detail, it challenged the foundational meaning of the elementary charge. And yet, the mathematical case for quarks was hard to ignore. The eightfold way had predicted an entire particle before it was discovered. The quark model organized every known hadron into clean families. The three-quark structure of the proton and neutron explained their observed properties. Every time physicists tested the model, it worked. So experimenters searched, accelerators smashed particles together, and physicists hunted through the debris for any particle carrying 1/3 or 2/3 of a standard charge. Millikan's oil drop technique was adapted for modern experiments. Cosmic ray archives were re-examined. The oceans were sampled. Cosmic rays hitting the ocean floor over millions of years should have left a trace of free quarks if they existed. Nothing. No fractional charge has ever been detected in a free particle, not in 60 years of searching. This result meant one of two things. Either quarks didn't exist as real physical objects, only as mathematical symbols, or quarks existed but were permanently locked inside hadrons, unable to escape under any circumstances. The confinement idea, that quarks are real but permanently imprisoned, made a specific prediction. If you fired a high-energy probe at a proton and looked carefully at what happened during the collision, not at what came out afterward, you might see evidence of internal structure even without freeing the pieces. That is exactly what the Stanford experiments were designed to test, and the results they produced were unambiguous in a way that settled the debate. The proton was composite. Something hard and point-like lived inside it. Whether those constituents were the quarks of Gell-Mann's model or something else entirely, the data showed clearly that the proton had an interior structure. But before those results could be understood fully, there was a deeper puzzle. How do you even see inside a proton? What kind of probe works at those scales? And what does it mean for a particle to be point-like when you're looking at distances 100,000 times smaller than the nucleus itself? The answer required a new way of thinking about what high-energy collisions actually reveal. In 1967, a machine in California started firing electrons at protons. The machine was the Stanford Linear Accelerator, a straight tunnel about 2 miles long, running beneath the hills south of San Francisco. It accelerated electrons to energies no lab had achieved before, and it aimed them at a hydrogen target, essentially a tank of protons. What happened in those collisions was recorded carefully, and what the recordings showed broke physics open again. The experiment was called deep inelastic scattering. The name describes what happens. The electron hits the proton and scatters, bounces away at an angle. Inelastic means the collision is not a clean bounce. Energy is transferred. The proton doesn't just recoil, it breaks up, producing a spray of other particles. Deep means the electron has enough energy to probe far inside the proton, at distances much smaller than the proton itself. Here is the key idea. When you fire a particle at something, the angles it scatters at tell you about the structure of what it hit. Fire an electron at a smooth, uniform sphere of charge, and the scattering follows a specific pattern. Gentle deflections, smooth curves, predictable distributions. Rutherford had used exactly this logic 56 years earlier to discover the nucleus. Now, the same logic was being applied one level deeper. If the proton were a smooth, uniform blob of positive charge, the electrons fired at it would scatter in a smooth, gentle pattern. The deflections would be small, the angular distribution would be predictable and bland. That is not what happened. Instead, the electrons scattered at large angles far more often than a smooth proton would allow. The pattern of deflections matched what you would expect if the electrons were sometimes hitting small, hard, point-like objects inside the proton and missing them most of the time, since most of the proton's volume is open space. It was Rutherford's gold foil experiment, scaled down by a factor of 100,000. The team running the experiments, led by Jerome Friedman, Henry Kendall, analyzed the scattering data over several years. The results were consistent and clear. Something hard and point-like was inside the proton. These internal constituents were initially called partons, a neutral term chosen deliberately because the experimenters didn't want to claim they had found Gell-Mann's quarks before the connection was firmly established. Over the following years, as more data came in and theorists worked through the implications, the partons and the quarks turned out to be the same objects. The mathematical properties that the scattering data required for the internal constituents matched the properties that Gell-Mann had assigned to quarks. The proton was composite. The neutron was composite. Every proton and neutron that had ever been called a fundamental particle was built from something smaller. Friedman, Kendall, and Taylor received the Nobel Prize in Physics in 1990. But confirming that something hard lived inside the proton was only the beginning of the real mystery. The hard things inside couldn't be pulled out. Every attempt to extract them failed in the strangest possible way. What came out instead of free quarks was something that nobody had predicted. The data from Stanford didn't arrive all at once. It built up over 6 years, from 1967 to 1973, one collision at a time. Millions of electrons fired, millions of scattering events recorded, and as the numbers accumulated, a picture emerged that nobody could argue with. Here is what the data actually showed. When an electron hits a smooth, uniform object, the probability of its scattering at a large angle drops off rapidly. Large deflections are rare. Small deflections are common. The distribution is smooth and predictable. Think of throwing a tennis ball at a pillow. Most throws produce gentle bounces. Nothing throws the ball back hard. When an electron hits something with hard internal structure, small, dense, point-like constituents spread through mostly open space, the pattern changes. Large angle scattering happens more often than it should. The electron occasionally hits one of the hard internal pieces, dead on, and gets thrown sideways at a sharp angle. The distribution develops a shape that betrays the presence of internal objects. The Stanford data showed the second pattern, definitively, but there was a subtlety that made the result even more powerful. The team didn't just measure scattering angles, they measured how the scattering pattern changed as they increased the energy of the electrons. And here, something remarkable appeared. For a smooth, extended object, increasing the electron's energy changes the scattering pattern in a specific way. The details of how the electron probes the structure shift with energy. But for point-like internal objects, The scattering pattern shows a property called scaling. The shape of the distribution stays roughly the same regardless of the energy used, because the things being hit are so small they look point-like at every energy level. The Stanford data showed scaling almost exactly. This was a stunning result. Scaling meant the constituents inside the proton behaved like point particles, objects with no size of their own at the scales being probed. They were not little balls with internal structure of their own. They were, at those distances, truly fundamental looking. A theorist named James Bjorken had actually predicted this scaling behavior before the experiments ran, using mathematical arguments about what quark-like constituents would produce. When the data matched his prediction, the theoretical and experimental sides of physics snapped together. The internal constituents were real. They were point-like. They carried fractions of the proton's momentum, and they interacted with the electron's electric field, which meant they carried electric charge. When theorists calculated what fraction of the proton's charge those internal objects carried, the answer came out consistent with the fractional charges Gell-Mann had assigned to quarks. The partons were quarks. The connection was firm. But one fact from the data puzzled everyone. The quarks inside the proton accounted for only about half of its total momentum. The other half was being carried by something that didn't interact with the electron at all. Something neutral. Something electrically invisible. Those invisible carriers of momentum were the gluons, the particles that carry the strong force between quarks. They were there all along, invisible to the electron but real enough to carry half the proton's energy. Finding the quarks was one revelation. The gluon hiding in the leftover momentum was another, and the force those gluons carried was unlike any force physics had encountered before. Richard Feynman gave the parton its name. He was already one of the most famous physicists alive when the Stanford results started coming in, and he moved fast to make sense of them. Feynman visited Stanford in 1968 and heard the early data from the scattering experiments. He immediately proposed a picture. During a high-energy collision, he suggested, the proton could be thought of as a stream of point-like constituents, each carrying some fraction of the proton's total momentum. The electron would scatter off whichever constituent it happened to hit. The scattering angles would reflect the hard, point-like nature of those hits. He called the constituents partons, a deliberately vague name. Feynman was careful not to claim they were quarks. The quark model was a separate theoretical framework, and connecting the two required more work. He wanted a word for the observed objects that carried no theoretical baggage until the evidence was clear. The parton model was simple and it worked. It explained the scaling behavior naturally. It explained why large-angle scattering happened more often than a smooth proton would allow. It predicted the shape of the momentum distributions inside the proton, and it gave experimenters a clean framework for interpreting the collision data. The connection to quarks came through careful analysis. If the partons had the spin properties of quarks, and if their number matched the 3 quarks per proton that Gell-Mann's model required, then partons and quarks were the same thing seen from different angles, one from theory, one from experiment. Every test confirmed the connection. By the early 1970s, the identification was complete. But the parton model also revealed something unsettling. The quarks inside the proton were not sitting still. They were moving constantly, exchanging momentum with each other, radiating and absorbing gluons. The proton was not a tidy bag of 3 quiet quarks. It was a seething, dynamic object. At any given moment, gluons were splitting into quark-antiquark pairs. Those pairs were annihilating back into gluons, and the 3 permanent quarks were constantly being buffeted by this internal storm. The 3 quarks that define a proton's identity, 2 up quarks and 1 down quark, are called valence quarks. But swimming alongside them at all times is a sea of short-lived quark-antiquark pairs, constantly popping in and out of existence. The proton is not a simple triplet. It is a complex, quantum mechanical object where 3 stable quarks ride a churning sea of temporary ones. This picture made the proton feel less like a tiny ball and more like a weather system, a permanent structure riding constant turbulence. Understanding that turbulence, and the gluons driving it, required a new theory, a theory that could explain how quarks interact, why they stay confined, and why the force between them behaves so differently from every other force in nature. That theory was coming, and when it arrived, it brought with it one of the strangest concepts in all of physics. Every instinct says that if you pull something hard enough, it comes apart. Pull a rope, and it stretches. Pull harder, and it snaps, leaving two separate pieces. Pull a molecule apart, and you get separate atoms. Pull an atom apart, and you get separate electrons. And a nucleus. At every level of matter, separation is possible if you apply enough force. Quarks break this rule completely. No matter how much energy you put into trying to separate two quarks, you will never get a free quark sitting alone in your detector. The reason involves something fundamental about how the strong force works. When you try to pull two quarks apart, the gluon field between them doesn't just stretch and weaken the way an electric field does. It holds tight. The energy stored in the gluon field between separating quarks grows as the distance increases. More separation means more energy stored in the field. At a certain point, enough energy has accumulated in that gluon field that the laws of physics do something extraordinary. Energy converts into matter. A new quark-antiquark pair materializes right in the space between the separating quarks. Suddenly, the single stretched connection snaps, but instead of leaving two free quarks, it leaves two complete bound pairs. Two mesons where one proton used to be. You pulled. You got more bound particles, not fewer. This process repeats. If you try again with more energy, you get more particle pairs. The strong force manufactures new matter rather than allowing a quark to exist alone. Nature is not hiding quarks from you. Nature is actively producing new matter to prevent their isolation. Physicists call this property confinement. Every quark that has ever existed has been confined inside a hadron. Every quark that ever will exist will be confined. The universe has never contained a free quark, at least not since the earliest moments after the Big Bang, when temperatures were high enough that the rules worked differently. Confinement is why the quark searches of the 1960s came up empty. Experimenters weren't missing free quarks in their data. Free quarks genuinely were not there. Every high-energy collision produced not isolated quarks, but jets of new hadrons, sprays of mesons and baryons created from the energy of the collision. Those jets are themselves evidence for quarks. The spray of particles produced in a high-energy quark-level collision forms along the original quark's direction of travel, like a shotgun blast following the direction of the shot. Physicists learned to read those jets the way a forensic scientist reads a crime scene, inferring the invisible quark from the trail of particles it left behind. Seeing the jet and knowing it traces back to a quark is one of the most indirect but certain detections in all of science. The quark leaves a fingerprint, even if it never steps into the open. Confinement explained why quarks had never been isolated, but it raised an even harder question. Why does confinement happen? What property of the strong force produces this behavior? The answer required a new theory, one that would eventually explain everything about how quarks interact. That theory came with a name nobody expected, and a concept so strange it took a generation of physicists to fully absorb. Picture a bar magnet. Cut it in half, and you don't get a separate North Pole and South Pole. You get two smaller magnets, each with its own north and south. The poles come in pairs, and they stay that way no matter how many times you cut. Quarks work on a similar principle, but far more dramatically. When a high-energy collision smashes into a proton with enough force to tear a quark away from its partners, the strong force field between them stretches. The field doesn't spread out like an electric field does, it stays narrow, a tube of force connecting the separating quarks. Physicists call this a flux tube. The flux tube carries enormous energy density. As the quarks move apart, The tube stretches, storing more and more energy per unit of length. The energy doesn't dissipate, it concentrates. Then it breaks. But breaking the flux tube doesn't free the quarks. At the moment of breaking, the energy in the tube converts into a new quark-antiquark pair. Each end of the broken tube now has a quark to connect to. Where one stretched connection existed, two shorter ones now exist, each binding its own pair of quarks. This process is called string breaking. The quark was never freed. Two new bound states appeared instead. In practice, at accelerator experiments, this process cascades. One high-energy quark produces multiple breaks, multiple new particles. The shower follows the original direction of the quark's momentum. By the time the process ends, a jet of pions, kaons, and other hadrons is flying through the detector, pointing back toward the spot where the original quark was struck. Scientists can measure those jets precisely. The energy of the jet equals the energy of the original quark. The direction of the jet traces the quark's path. The number of particles in the jet reflects the strength of the interaction. Everything about the original quark can be inferred without ever catching one directly. This indirect measurement became the standard method. Over decades, physicists used jet analysis to study quarks in extraordinary detail. Their masses, their spin, their interactions, all inferred from the particle showers they leave behind. One of the most striking confirmations of the gluon came in 1979 at a German accelerator called Petra. An electron-positron collision produced 3 jets instead of 2. 2 jets from the quark-antiquark pair, and a third jet from a gluon radiated by one of them. 3 jets, 3 directions, 3 sets of particles. The third jet was the gluon's signature. Until that moment, gluons were inferred. After that event, they were seen not directly but through the unmistakable mark of their decay products. Matter had revealed another hidden layer. Inside the proton were quarks. Binding those quarks were gluons. Both were unremovable from the systems they inhabited. The theory that explained all of this, why the flux tube forms, why string breaking occurs, why gluons exist, why confinement is absolute, was developed through the 1970s. It gave the strong force a name, a mechanism, and a mathematical language precise enough to calculate predictions with. It also introduced a property of quarks, so bizarre that it needed an entirely new word to describe it. Every fundamental force in nature works through a carrier particle. The electric force is carried by photons, particles of light. Even when no light is visible, 2 charged particles exchanging electric force are passing photons back and forth invisibly. Gravity in the framework of modern physics is believed to be carried by gravitons, though none has been directly detected. The weak nuclear force, responsible for certain types of radioactive decay, is carried by heavy particles called the W and Z bosons. The strong force has its own carrier, the gluon. Gluons shuttle back and forth between quarks inside a proton, carrying the strong force that keeps the quarks bound together. Every moment a proton exists, its 3 quarks are absorbing and emitting gluons at a furious rate. The gluon field is not a static thing, it is a constant exchange, a continuous handoff of force between the quarks. But gluons have a property that makes them far stranger than photons or any other force carrier. Gluons interact with each other. Photons, which carry the electric force, do not interact with other photons under normal conditions. 2 beams of light pass through each other without deflecting. Light doesn't stop light. This is why electromagnetism is mathematically tractable. The carrier of the force doesn't carry the force itself. Gluons are different. They carry color charge, the property that defines participation in the strong force. Because they carry color charge, gluons are themselves subject to the strong force. Gluons interact with quarks and with other gluons. This self-interaction is the reason the strong force behaves so differently from electromagnetism. When an electric field spreads from a charge, it expands outward in all directions, growing weaker with distance because the field lines spread over a larger area. Gluons, interacting with each other, pull the strong force field into a narrow tube instead of letting it spread. The flux tube that forms between separating quarks exists precisely because gluons attract each other and hold the field lines together. That same self-interaction is part of why confinement occurs. The strong force doesn't spread and weaken, it stays concentrated. Gluons also carry a combination of color and anticolor charge. There are 8 distinct types of gluon, corresponding to 8 possible color-anticolor combinations allowed by the mathematics of the theory. This is very different from the photon, which comes in one type and carries no charge. The existence of 8 gluon types is not arbitrary. It follows from the mathematical symmetry group that underlies the theory of the strong force. The number 8 is a consequence of the mathematics, not a coincidence. Because gluons have mass equal to 0, they travel at the speed of light. But unlike photons, they can never escape from hadrons. A gluon emitted by a quark is immediately subject to the strong force itself, and the field it creates helps confine it and the quarks together. The gluon was indirectly confirmed in that 3-jet event in 1979. Since then, gluon behavior has been studied in enormous detail at accelerators around the world. The measurements match theoretical predictions with extraordinary precision. But making those predictions required a theory that could handle gluon's self-interactions mathematically. Building that theory was one of the most demanding achievements in the history of physics. When physicists developed the theory of electromagnetism at the quantum level, they built a framework called quantum electrodynamics. It is one of the most precise theories in all of science. Its predictions match experimental measurements to more than 10 decimal places. The key reason it works so well is that the carrier of the electric force, the photon, does not interact with other photons. The mathematics stays manageable. The strong force is a different story. Because gluons interact with each other, the mathematics of the strong force theory is far harder. Every calculation has to account not just for quarks interacting through gluons, but for gluons interacting with other gluons, and those gluon-gluon interactions producing more gluons, which interact further. The chains of interactions multiply rapidly. In quantum field theory, calculations are done using a technique called perturbation theory. The idea is that interactions can be broken into a series of increasingly complex terms, and if the coupling, the strength of the interaction, is small, the series converges quickly. The first few terms give a good approximation, and the rest are negligible. This works beautifully for electromagnetism. The coupling of the electric force is small enough that calculations converge fast. For the strong force, the coupling is large at low energies. The energy scales relevant to nuclear binding and quark confinement. A large coupling means the series of terms doesn't converge quickly. Each additional term matters. Cutting off the calculation after a few terms gives a bad answer. Including more terms makes the problem more complex. At high energies, something called asymptotic freedom saves the calculation. At very short distances, the coupling of the strong force actually becomes small. Quarks interact more weakly the closer together they are. This was discovered in 1973 by David Gross, Frank Wilczek, and David Politzer, who shared the Nobel Prize for it in 2004. Asymptotic freedom means that at high energies, perturbation theory works for the strong force, and precise calculations are possible. That is why the Stanford experiments, which probed quarks at high energy, could be compared successfully with theoretical predictions. At those energy scales, the mathematics was tractable. At low energies, the scales relevant to how quarks bind into protons and how protons bind into nuclei, the coupling is large, perturbation theory fails, and direct calculation becomes extremely difficult. Physicists turn to a different approach called lattice quantum chromodynamics. where space-time is replaced by a computational grid, and the equations are solved numerically with powerful computers. Lattice calculations have confirmed confinement, reproduced the masses of protons and neutrons from first principles, and produced increasingly precise results, but they are computationally intensive. A single high-precision calculation can require months on some of the most powerful computers in existence. This is why the nucleus took so long to understand fully. The difficulty was not only experimental, the theory required mathematics that pushed against the limits of what physicists could calculate. And in some regimes, those limits still have not been fully crossed. The exact mechanism of confinement, why the strong force produces it from first principles, remains one of the deepest open problems in theoretical physics. By the early 1970s, the pieces were in place. Quarks had been confirmed experimentally. Gluons were inferred from momentum distributions. The strong force had a known property, asymptotic freedom, that allowed precise calculation at high energies. A complete theoretical framework was needed to tie everything together. That framework arrived and was named quantum chromodynamics. Physicists almost universally shorten it to QCD. QCD is the theory of how quarks and gluons interact through the strong force. It describes every aspect of quark behavior, how they bind into hadrons, how gluons carry force between them, how the force changes with distance and energy, why quarks are confined. The theory was built on a mathematical structure called a non-abelian gauge theory. That term describes a specific type of symmetry that the theory obeys. The same general framework underlies the theories of all the fundamental forces. What differs between them is the specific symmetry group involved. For the electric force, the symmetry group is simple: one type of charge, one type of carrier, no self-interaction. For the strong force, the symmetry group is more complex, called SU3. This more complex symmetry is what gives rise to the 8 types of gluons, the 3 types of color charge, and the self-interaction among gluons. QCD made predictions that could be tested. At high energies, it predicted the specific pattern of quark and gluon behavior seen in deep inelastic scattering. It predicted how the strong coupling changes with energy, a measurable quantity called the running coupling constant. It predicted the existence and properties of gluon jets. Every prediction was tested. The theory also provided a natural explanation for asymptotic freedom. The self-interaction of gluons produces an effect opposite to what happens in electromagnetism. In electromagnetism, vacuum fluctuations tend to screen charge, weakening the force at longer distances. In QCD, gluon self-interactions produce an anti-screening effect at short distances, weakening the coupling as quarks get closer. This is asymptotic freedom, and it falls directly out of QCD's mathematical structure. QCD also gave confinement a qualitative explanation, even if the full mathematical proof remains elusive. The same gluon self-interactions that produce asymptotic freedom at short distances produce strong coupling at long distances. As quarks separate, the coupling grows. The flux tube forms. String breaking occurs. Quarks remain confined. The theory unified the understanding of the strong force at 2 levels simultaneously. At the quark level, QCD explains how quarks bind into protons and neutrons through gluon exchange. At the nuclear level, the force between protons and neutrons, the one holding the nucleus together, emerges as a residual effect of QCD, acting between composite objects, the way van der Waals forces act between neutral molecules. 2 levels of physics, one underlying theory. The proton and neutron were no longer fundamental, they were complex bound states of quarks and gluons, described by one of the most mathematically rich theories ever constructed. And the nucleus sitting at the center of every atom was built from those composite objects, held together by the echo of a force operating 1 level deeper. The journey from Rutherford's gold foil to QCD had taken 60 years. The layers of matter had been peeled back, one by one, until the deepest accessible level had been reached. But the deepest accessible level was still full of mysteries. Quarks carry electric charge. Everyone who has heard of protons and electrons knows about electric charge, but quarks carry a second type of charge as well, one that has nothing to do with color, despite its name. It is called color charge, and understanding it is essential to understanding why QCD works the way it does. The name was chosen as a metaphor. In the 1960s, physicists noticed a problem with the quark model. Certain hadrons seemed to require 3 identical quarks in the same quantum state. A particle called the delta++ baryon, for example, appeared to contain 3 up quarks with the same spin. But quantum mechanics has a strict rule, the Pauli exclusion principle, that says 2 identical fermions cannot occupy the same quantum state simultaneously. 3 identical up quarks in the same state should be forbidden. To resolve this, physicists proposed that quarks carry an additional quantum property that could distinguish otherwise identical quarks. They gave this property 3 values and named them red, green, and blue, borrowing color terms as a convenient label. The 3 up quarks in the delta++ could now be distinguished: 1 red, 1 green, 1 blue. The Pauli exclusion principle was satisfied. The name color is purely a label. Quarks are not actually red, green, or blue. No quark has ever been seen by any eye or instrument. The color label is a way of counting distinct quantum states. But the label turned out to carry deep mathematical meaning. When physicists built QCD around the symmetry that rotates between these 3 color states, the theory naturally produced the 8 gluons, the self-interaction, the asymptotic freedom, and the confinement that matched experiment. Color was not just a bookkeeping trick. It was the foundation of the whole theory. There is a rule in QCD: every observable particle must be color neutral. Protons and neutrons achieve this by containing 1 red, 1 green, and 1 blue quark. The combination cancels to colorless, by analogy with how red, green, and blue light mix to white. Masons achieve colorlessness by pairing a color with its anti-color, a red quark with an anti-red quark, for example. This color neutrality rule is directly connected to confinement. Isolated color charges are not permitted to exist in the observable world. Every combination of quarks and gluons that can exist as a stable particle must be colorless overall. This automatically forbids free quarks, which carry a single color charge. The strong force acts on color charge the way the electric force acts on electric charge. But because color comes in 3 types instead of 1, and because gluons themselves carry color, the resulting theory is far richer and more complex than electromagnetism. Color charge is invisible, unmeasurable directly, and carries a name that describes nothing visual. And yet it is the reason every nucleus in the universe holds together. Without color charge, quarks would not interact through the strong force. Without the strong force, protons would not form. Without protons, nuclei would not exist. Without nuclei, atoms would not form. Without atoms, nothing in the universe as we know it, not planets, not stars, not life, would be here. Color charge, for all its strange name, is the invisible thread that holds reality together. The strong force plays 2 roles in nature. Both are real, both are essential, and they operate at very different scales, which is part of why it took so long to understand that they were related. The first role is binding quarks inside protons and neutrons. At this scale, QCD is the full story. Quarks carry color charge, gluons carry the force between them, and the result is a proton or neutron, a colorless stable composite particle a few femtometers across. The second role is binding protons and neutrons into the nucleus. At this scale, something different appears to be happening. Protons and neutrons are already colorless. They don't carry net color charge. So how does the strong force act between them at all? The answer involves a concept called the residual strong force, and the best analogy is the behavior of neutral atoms. Water molecules carry no net electric charge. Hydrogen and oxygen atoms within each molecule are bound by shared electrons, but the molecule as a whole is electrically neutral. When two water molecules get close, they should feel no electric force from each other, and yet they do attract, slightly. The charge distributions within each molecule are asymmetric enough that at close range, the positive charge centers and negative charge centers interact weakly. This residual electrical interaction is called the van der Waals force. It is a leftover effect of the electric force acting between neutral objects at close range. The nuclear force between protons and neutrons is the exact same concept applied to color charge. A proton is colorless overall, but it has internal color, 3 quarks, each carrying 1 color. At the distances inside a nucleus, a few femtometers, the color fields of neighboring protons and neutrons overlap slightly. The colorless exterior of each nucleon leaks a residual color interaction to its neighbors. That leakage is the nuclear binding force. It is QCD acting at the nucleon scale rather than the quark scale. The particles that mediate this residual force at the nucleon level are called pions and other mesons, the particles Yukawa predicted in 1935. At the deeper level, those pions are themselves quark-antiquark bound states, so the nuclear force is ultimately QCD all the way down, but the way it appears at the nuclear scale looks like pion exchange rather than gluon exchange. This layered picture, QCD at the quark scale, residual force at the nucleon scale, explains something that puzzled early nuclear physicists. The nuclear force has a short range of about 1 femtometer. The residual force naturally falls off faster than the underlying QCD force, because the color fields of composite objects partially cancel at larger distances. The short range of the nuclear force is a geometric consequence of the colorless structure of protons and neutrons. The nucleus is held together by a shadow of the force that holds protons and neutrons together. A shadow, but powerful enough to bind every element in the periodic table. Most illustrations of the nucleus show it as a tight cluster of balls, protons and neutrons packed together like a bunch of grapes, sitting quietly in the center of the atom. That picture is useful and completely misleading. The nucleus is not static. It is a quantum mechanical system in constant motion, and its behavior is far richer than any ball cluster image suggests. Protons and neutrons inside a nucleus occupy specific quantum states, governed by rules similar to the ones that govern electrons around the atom. Just as electrons exist in energy levels and orbitals, nucleons occupy nuclear energy levels. Nucleons fill these states from the lowest energy upward, following quantum rules that forbid two identical nucleons from sharing the same state. This quantum structure explains patterns in nuclear stability. Nuclei with certain numbers of protons or neutrons, 2, 8, 20, 28, 50, 82, 126, are unusually stable. These are called magic numbers. They correspond to completely filled shells of nuclear energy levels, the same concept as the filled electron shells that make noble gases chemically inert. Beyond energy levels, nuclei can change shape. Many nuclei are approximately spherical. Others are stretched into elongated shapes, like an American football. Some are compressed into flattened shapes, like a lens. These shapes are not fixed. They reflect the average distribution of nucleons in their quantum states. Nuclei can also vibrate. The surface of a nucleus can oscillate, swelling and compressing in regular patterns, like a drop of liquid wobbling in space. They can also rotate. A deformed nucleus spinning in space produces rotational energy levels that physicists can measure through the gamma rays emitted when the nucleus drops from one rotational state to a lower one. These vibrations and rotations are real physical motions. They have measurable energies and specific quantum properties. Nuclear physicists have mapped them in hundreds of different nuclei. Nuclei can also suddenly change structure altogether. Some nuclei exist in excited states, higher energy configurations that decay to the ground state by releasing a gamma ray. Others undergo a shift where protons and neutrons rearrange themselves dramatically, changing the nucleus's shape or pairing structure. The nucleus is also influenced by the quantum vacuum around it. Virtual particle pairs pop in and out of existence inside the nucleus, continuously affecting its properties in subtle but measurable ways. All of this complexity lives in an object smaller than a single protein molecule. The nucleus is a quantum many-body system, a collection of strongly interacting particles governed by rules that have no everyday analog. Its full description sits on top of QCD, which itself is one of the hardest theories in physics to calculate. Nuclear physicists spend careers studying single nuclei. Every new stable nucleus investigated reveals new quantum behavior, new deformations, new modes of excitation. The nucleus that Rutherford discovered as a dense dot in 1911 turned out to be an entire world of its own. And at the extreme edges of that world, in nuclei pushed far from stability, matter begins to behave in ways that challenge everything the standard picture predicts. Most atoms in the everyday world have survived for billions of years. Iron, carbon, oxygen, nitrogen. The nuclei in your body and in the rocks under your feet are ancient and stable. They exist because their particular ratio of protons to neutrons makes them energetically comfortable. Shift that ratio far enough in either direction, and the nucleus becomes unstable. It will decay, sometimes quickly, sometimes slowly, but always inevitably. The limit of how far you can shift the ratio and still have a nucleus that holds together at all, even briefly, defines the edges of what physicists call the nuclear landscape. Beyond those edges, nuclei simply don't exist. Add one more neutron to an already neutron-rich nucleus, and it falls apart almost instantly. These extreme nuclei are called exotic nuclei, and they behave in ways the standard nuclear models didn't predict. One of the strangest examples involves nuclei with a massive excess of neutrons. In a normal nucleus, protons and neutrons are distributed through roughly the same volume. In extremely neutron-rich nuclei, the excess neutrons form a diffuse cloud extending far beyond the tight proton-neutron core. Physicists call this a neutron halo. The first confirmed neutron halo nucleus was lithium-11, discovered in the 1980s. Lithium normally has 3 protons and 4 neutrons. Lithium-11 has 3 protons and 8 neutrons, far more neutrons than the standard lithium nucleus can stably hold. 2 of those excess neutrons form a halo that extends to nearly 3 times the radius of the core. The overall nuclear radius of lithium-11 is roughly the same as a carbon nucleus, despite having far fewer total particles. The halo exists because the 2 outermost neutrons are only weakly bound. Their quantum wave functions extend far outside the nuclear core. They are present, they are part of the nucleus, but they hover at enormous distances relative to the nuclear scale. Studying exotic nuclei requires producing them in the first place, which means running them through an accelerator and catching them before they decay. Some exotic nuclei live for only milliseconds, some for fractions of a millisecond. Experiments designed to study them have only a tiny window before the nucleus transforms into something else. Proton-rich exotic nuclei behave differently. With too many protons and not enough neutrons, the electric repulsion among the protons overcomes the nuclear binding. Some proton-rich nuclei decay by emitting a single proton directly. A proton simply tunnels out through the energy barrier and escapes. Exotic nuclei also probe the limits of nuclear models. Theories built on the behavior of stable nuclei don't always predict exotic behavior correctly. The shell structure of magic numbers can shift. Energy levels reorder. Properties that seem fixed in stable nuclei become fluid near the edges of stability. Every exotic nucleus studied pushes the theoretical models and forces them to improve. And the most extreme nuclear environment in the universe, far beyond anything achievable in a laboratory, exists not in an accelerator, but in the remnant of a dead star. What matter does at that extreme density is one of the most active frontiers in all of physics. Radioactive decay sounds like a process happening to the nucleus from outside, but it comes entirely from within. It is the nucleus resolving an internal instability, shedding energy, rearranging its contents, or throwing out pieces it can no longer hold. There are several distinct ways a nucleus can decay, and each one tells a story about what is happening inside. Alpha decay is the most visually intuitive. A nucleus ejects an alpha particle, 2 protons and 2 neutrons bound together, and becomes a lighter nucleus in the process. The alpha particle forms inside the nucleus before it escapes. It is not waiting to be expelled from outside. It assembles internally from existing nucleons and then tunnels through the energy barrier surrounding the nucleus. The tunneling is a quantum effect. Classically, the alpha particle should not be able to escape. The nuclear binding energy creates a barrier it doesn't have enough energy to climb over. But in quantum mechanics, particles have wave-like properties that allow them to penetrate through barriers with a small but non-zero probability. Given enough time, the alpha particle tunnels out. The probability of tunneling per unit time determines the decay rate. Some alpha emitters take billions of years to decay, others take microseconds. The barrier height and thickness determine which. Beta decay is more fundamental. In one form, a neutron inside the nucleus transforms into a proton, emitting an electron and a particle called an antineutrino. This process is mediated by the weak nuclear force, the same force responsible for certain types of particle interactions. At the quark level, a down quark inside the neutron converts into an up quark, changing the neutron into a proton. The transformation changes the element. Carbon-14 decays to nitrogen-14 this way, which is the basis of radiocarbon dating. In the other form of beta decay, a proton converts into a neutron, emitting a positron and a neutrino. This happens in proton-rich nuclei, where shedding a proton reduces the electric repulsion enough to stabilize the result. Gamma decay doesn't change the nucleus's composition at all. A nucleus in an excited energy state drops to a lower state and releases the energy difference as a gamma ray, a high-energy photon. The nucleus keeps all its protons and neutrons, but loses energy. It's the nuclear equivalent of an atom releasing light when an excited electron drops to a lower level. Each decay mode is the nucleus finding a more stable configuration. The instability might come from too many neutrons, too many protons, too much overall energy, or a shape that doesn't minimize the system's energy. The nucleus decays until it reaches a configuration that is stable, or until it transforms into a different element, that is. The chain of decays from uranium-238 ends at lead-206. Along the way, the nucleus sheds alpha particles and undergoes beta decays across 14 steps, spanning timescales from microseconds to billions of years. Every radioactive nucleus in nature is in the middle of that kind of journey, working toward a stable end, one rearrangement at a time. The densest nuclei on Earth are still mostly empty space compared to what sits at the center of a neutron star. When a massive star reaches the end of its life, its core collapses in a fraction of a second. The outer layers explode outward in a supernova. The inner core is crushed by its own gravity with such extreme force that something remarkable happens. Electrons are forced into protons. The electric charges cancel. Protons become neutrons. The entire stellar core transforms into a sphere of neutron-rich nuclear matter roughly 10 miles across. That sphere is a neutron star. The density inside a neutron star is close to the density of an atomic nucleus. The matter inside is packed so tightly that a single teaspoon of neutron star material would weigh roughly 4 billion tons. The entire mass of the Sun compressed into a ball the width of a city. At these densities, the rules that govern ordinary nuclear matter may no longer apply. In a normal nucleus, protons and neutrons maintain their identities. They are composite objects, 3 quarks each, but the quarks stay inside their respective nucleons. there is enough space between nucleons that each one remains distinct. Deep inside a neutron star, the spacing between nucleons shrinks towards zero. At extreme enough density, neighboring nucleons may begin to overlap. The quarks inside them are no longer clearly assigned to one proton or neutron. The distinction between individual nucleons may dissolve into a continuous fluid of quarks. Physicists call this state quark matter or quark-gluon plasma. It is a phase of matter where quarks are no longer confined inside hadrons, but roam more freely through the bulk material. Whether this transition actually occurs at neutron star densities is not yet known for certain. The densities at the centers of the most massive neutron stars may be high enough to push matter into this exotic phase. Or nuclear matter may find other ways to rearrange itself, through exotic particles called hyperons, through kaon condensates, or through other configurations that theoretical models have predicted but not confirmed. The answer matters enormously. The structure of neutron stars determines how they vibrate, how they merge when two of them collide, and what gravitational waves those mergers produce. In 2017, the LIGO and Virgo detectors captured gravitational waves from two neutron stars colliding. The precise shape of those waves carries information about the density and stiffness of neutron star matter at its core. Scientists are currently extracting that information. The data is constraining the models. The answers will tell us what happens to nuclear matter at densities beyond anything a laboratory on Earth can produce. The nucleus began as a dot in the center of an atom. At its extremes, it becomes the entire body of a dead star, and those stars are teaching us where the known physics of nuclear matter runs out. Hydrogen is the simplest atom. One proton, no neutrons. It formed in the first minutes after the Big Bang, when the universe was hot enough to push protons and neutrons together. For the first few minutes, the whole universe was a nuclear reactor. In those first minutes, nuclear reactions built helium from hydrogen and small amounts of lithium and beryllium. Then the universe expanded and cooled, and the nuclear reactions stopped. For hundreds of millions of years, the universe contained mostly hydrogen and helium, and almost nothing else. Every other element, carbon, oxygen, iron, gold, uranium, had to be built later, inside stars. A star is a nuclear furnace held in balance by two competing forces. Gravity pulls inward, the pressure from nuclear reactions pushes outward. As long as the reactions continue, the star holds its shape. In the core of a star like the Sun, hydrogen nuclei fuse into helium. 4 protons combine, shedding 2 positive charges through beta decay and become a helium nucleus. The mass of the helium nucleus is slightly less than the mass of the 4 protons that went into it. That missing mass is released as energy, the light and heat of the star. When hydrogen runs out, the core contracts, heats up, and helium begins to fuse into carbon and oxygen. In more massive stars, the process continues up the periodic table. Carbon fuses into neon and magnesium, oxygen into silicon and sulfur. Each stage produces heavier nuclei and releases energy, though less efficiently as the elements get heavier. Iron is where the ladder stops. Fusing iron releases no energy, it consumes energy. Once a star's core fills with iron, the nuclear reactions can no longer push back against gravity. The core collapses in under a second. The supernova explodes. In the explosion, the energy and neutron flux are extreme enough to drive nuclear reactions that produce elements heavier than iron. Gold, platinum, uranium, all forged in the violence of collapsing stars and neutron-star mergers, scattered across space, eventually incorporated into new star systems and planets. The calcium in your bones was fused in the core of a star that died before the sun existed. The iron in your blood was forged in a stellar collapse. The oxygen you breathe was built in a fusion chain that ran for millions of years before the star that made it exploded. The nucleus is not just a physics problem, it is the mechanism that built the material universe. Every atom heavier than lithium passed through a nuclear furnace at some point in cosmic history. The strong force, operating at femtometer scales, is responsible for the material variety of everything that exists. Rutherford found a tiny dense dot. That dot turned out to be the engine of cosmic chemistry. Physics has explained a great deal. The nucleus was discovered. Its contents were identified. The force holding it together was measured and mapped. The quarks inside protons and neutrons were confirmed through scattering experiments. QCD was built and tested and verified to extraordinary precision. And yet, one of the most basic questions about the strong force remains unanswered at the deepest level. Why are quarks confined? The answer at the qualitative level is understood. Gluons self-interact. The force field between separating quarks doesn't spread out. It stays in a tube. The energy in that tube grows until string breaking occurs and new particles appear. Confinement is a consequence of gluon self-interaction and the way the QCD field behaves at long distances. But the rigorous mathematical proof of confinement, a demonstration from the fundamental equations of QCD that quarks cannot exist as free particles valid in all cases and at all energy scales, does not yet exist. This is not a minor gap. The Clay Mathematics Institute listed the problem of proving confinement from QCD as one of the 7 Millennium Prize problems, among the most important unsolved problems in mathematics. A correct proof comes with a $1 million prize attached. As of now, the prize remains uncollected. The difficulty is technical and deep. QCDs, straightforward to work with at high energies, where asymptotic freedom makes the coupling small and perturbation theory converges. At low energies, where confinement and nuclear binding operate, the coupling is large, perturbation theory fails, and exact calculations require different methods. Lattice QCD, which solves the equations numerically on a computational grid, has confirmed confinement in simulations. Simulated quarks stay confined in lattice calculations. This is strong numerical evidence that QCD produces confinement. But numerical evidence and mathematical proof are different things. A simulation shows that something happens. A proof explains why it must. The gap matters beyond mathematics. A full proof of confinement would likely provide new insights into the structure of strongly coupled field theories, theories that appear in condensed matter physics, in models of the early universe, and in approaches to quantum gravity. The tools developed to prove confinement would have consequences far outside nuclear physics. There is also the connected question of what happens to confinement at extreme temperatures and densities. In the very early universe, temperatures were high enough that quarks were not confined. They moved freely through a quark-gluon plasma. As the universe cooled, confinement switched on. Quarks bound into hadrons in a transition called the QCD phase transition. The precise nature of that transition and the conditions that trigger it are still actively studied. The deepest layer of the nucleus remains partly open. The theory that explains it is confirmed, powerful, and precise at high energies. At low energies, it still guards its secrets. Ernest Rutherford died in 1937. He never knew about quarks. He never knew about gluons or asymptotic freedom or color charge. He died knowing the nucleus existed, knowing it contained protons and neutrons, and knowing that some force held it together. He didn't know what that force was made of. He had found the first door. Behind it were many more. That is the real story of the nucleus. It is a story about layers. Each layer was found using tools built specifically for that scale. Gold foil for the nucleus, the Stanford accelerator for quarks, lattice computers for confinement. Each layer required not just new experiments, but new mathematics and new ways of thinking about what matter even is. In 1911, matter had a nucleus. In 1932, the nucleus had protons and neutrons. In the 1960s, protons and neutrons had quarks. In the 1970s, quarks had a complete theory, QCD, that explained how they interact and why they stay hidden. Each answer created new questions. Each discovery pushed the mystery one level deeper. And the pattern itself is the lesson. When science finds something small, something smaller tends to be inside it. The atom seemed fundamental until the nucleus appeared. The nucleus seemed like the bottom until protons and neutrons turned out to be composite. The proton seemed like the end point until quarks were found inside it. Whether quarks themselves have inner structure is unknown. Current experiments show no evidence that they do, but current experiments have limits. The universe does not announce its layers in advance. It hides them behind the resolution of the instruments available. Every generation of scientists thought they were close to the bottom. Every generation found another floor below the one they stood on. This should not produce despair. It should produce awe. The fact that a team in England in 1909 could fire particles at gold foil and set in motion a chain of discovery that eventually mapped the interior of a proton, a chain that took 60 years, multiple Nobel Prizes, machines 2 miles long, and some of the hardest mathematics ever written, is one of the most extraordinary things humanity has ever done. The nucleus is smaller than anything you can see, feel, or touch. It exists in conditions of force and density that have no analogue in daily life. Its contents obey rules that make no intuitive sense, and yet physics cracked it open, layer by layer, using nothing but careful measurement, disciplined thinking, and the refusal to accept incomplete answers. Every atom in your body contains a nucleus. Every nucleus is held together by the strong force. Every strong force interaction traces back to quarks and gluons following the rules of QCD, and QCD sits on top of a proof that hasn't been written yet, a final explanation for why the quarks inside you can never come out. The universe built you from pieces that refuse to be separated. That is, on reflection, a remarkable thing to be made of.